Imagine a place where you could live forever. A place where you can travel to another galaxy in the blink of an eye, or become invisible with just a flick of a switch. You're able to control everything around you using only your thoughts. You could travel back in time to witness historical moments or jump into the future, changing what happens next. Impossible, right? These ideas may sound like dreams, but what if I told you that some of these impossibilities might not be as impossible as we once thought? The story of human progress is full of things once deemed impossible. Flying in the sky like birds? Impossible. Touching the moon? Absolutely out of the question. And yet, here we are, flying across continents and having walked on the moon. These milestones remind us that the boundaries of the possible and impossible aren't as rigid as they seem. Today, we'll take a journey into the physics of the impossible, where we'll explore not only what the laws of physics tell us about what's possible, but also how those limits are constantly shifting. We'll see how some impossibilities are closer to becoming reality, while others remain distant dreams, or even forever unattainable. But remember, just because something seems impossible today doesn't mean it will be tomorrow. Once upon a time, people believed that heavier-than-air flight was impossible. The scientific consensus was clear. Birds could fly because they were light, not because of any special forces. The idea that a machine, something made of metal, could ever soar like a bird seemed absurd. Yet, in 1903, the Wright brothers made the impossible possible, and the world changed forever. But the story doesn't stop with flight. Throughout history, we've had a long list of impossibilities that science has overturned. Think about it. The telephone, radio waves, or even electricity. At one point, all of these were thought to defy the natural laws of the time. So, what does impossible really mean? In the world of physics, something is labelled impossible when it violates the known laws of nature. For example, according to our current understanding, you can't build a machine that can produce energy forever without losing some to heat, a perpetual motion machine. It's not just hard to do, it's physically impossible according to the laws of thermodynamics, but those laws are based on our current knowledge. The key phrase is current knowledge. Science is always evolving, and with each breakthrough we unlock new doors. So when we talk about what's impossible today, we have to ask ourselves, is it truly impossible, or do we just not understand it yet? The laws of physics serve as a rulebook for the universe. They define what is possible within the fabric of space, time, and matter. But these laws weren't always clear. Isaac Newton gave us the first set of universal laws, rules that described how objects move and how gravity works. Newton's laws were so powerful that for centuries we believed they were absolute. And then along came Albert Einstein, who showed us that the universe was far more complex. With his theory of relativity, Einstein redefined our understanding of space, time, and even the speed of light. He didn't break Newton's laws, he expanded them, showing that they were just part of a bigger picture. What these scientific revolutions teach us is that the boundaries of what's possible are flexible. What was impossible in Newton's time, like time slowing down as you approach the speed of light, became part of the fabric of reality after Einstein. This constant expansion of knowledge brings us to a fascinating concept. There are different classes of impossibility. Physicists often divide impossibilities into three broad classes. These classes help us understand whether a concept that seems impossible today could one day become reality, or whether it's truly out of reach. Class 1 impossibilities are technologies that are impossible today, but they don't violate any known laws of physics. With enough time, money and research, we might be able to achieve them. Take invisibility, for example. We've already started developing metamaterials, substances that can bend light around an object, making it invisible to the naked eye. It's not perfect yet, but it's a taste of what might come. Or consider teleportation. While we may not be teleporting people like in science fiction, scientists have already teleported quantum information using quantum entanglement. One day, perhaps we'll find a way to teleport physical objects across space. Class 2. Impossibilities are technologies or phenomena that sit on the edge of our understanding. They might be possible, but they require a deeper understanding of physics than we currently have. Think about time travel. According to Einstein's relativity, time can stretch and warp, and in certain conditions, such as near a black hole, time might even loop back on itself. Then there's the concept of parallel universes. Quantum physics hints that every decision and every moment might branch off into a new universe where a different version of events unfolds. These ideas are on the cutting edge of science, just beyond our reach, but not entirely out of the question. Finally, we have Class 3 impossibilities. These are things that, according to everything we know today, truly break the laws of physics. Take perpetual motion machines, for instance. They violate the laws of thermodynamics, which dictate that energy is always lost in the form of heat. Or the concept of faster-than-light travel, which contradicts Einstein's theory that nothing can travel faster than light. These are concepts that seem truly, fundamentally impossible. But is anything truly impossible? Science is about exploring the unknown, and our understanding of the universe is constantly evolving. What seems impossible today might just be a question we haven't learned how to ask yet. One of the most fascinating aspects of science is how often fiction leads the way. Science fiction has always inspired scientists to dream big and ask bold questions. Think about the communication devices in Star Trek. They were pure fantasy when the show aired in the 1960s. Today, we carry smartphones in our pockets that are even more powerful. Even space travel, once confined to the pages of novels, became reality when humanity stepped onto the moon. Fiction dares us to dream of the impossible, and science works to make those dreams come true. In the same way, today's science fiction, whether it's teleportation, time travel, or parallel universes, could inspire the breakthroughs of tomorrow. By imagining the impossible, we open the door to innovation, and who knows what future discoveries will make today's impossibilities a reality. So, are there limits to what we can achieve? Maybe, maybe not. The journey from impossible to possible has always been one of the most exciting parts of human exploration. As we dive deeper into the world of Class 1, 2 and 3 impossibilities, remember, the future is shaped by those who dare to challenge the boundaries of what we know. And sometimes those boundaries are meant to be broken. Imagine walking down a crowded street, completely invisible. You can see everything around you, but no one knows you're there. It sounds like the stuff of fantasy, right? Well, not for long. Invisibility, once confined to myths and science fiction, is now on the cutting edge of modern science. Through the wonders of optical physics and revolutionary materials called metamaterials, scientists are making invisibility a reality. But how close are we to truly mastering the art of vanishing? Let's take a look at how far we've come and where invisibility could take us next. At the heart of invisibility lies the science of light. You see, visibility is all about how light interacts with objects. When light hits something, like your hand, it scatters in different directions, and that scattered light reaches your eyes, allowing you to see the object. But what if you could bend light around an object, preventing it from reaching your eyes? That's where the magic of invisibility begins. This concept isn't just a dream anymore. Scientists have developed materials called metamaterials, which can control and manipulate light in ways that nature cannot. These metamaterials are designed to bend light waves around an object, essentially guiding the light as if the object weren't there. The result is that the object becomes invisible to the observer. But how does it work? These metamaterials have a unique structure, smaller than the wavelength of light, that allows them to guide light around the object and continue on its path as if it had never encountered anything. Think of it like water flowing around a rock in a stream. The rock itself remains in place, but the water flows around it undisturbed. This is how metamaterials work with light, bending and twisting it around an object so that to an outside observer, the object seems to vanish. This control over light is the first step in making invisibility a scientific reality. The journey toward invisibility has already begun in labs across the globe. Scientists have successfully developed small-scale cloaking devices, proving that invisibility is no longer just a dream, it's a reality in controlled environments. One of the most notable experiments comes from a team that managed to cloak a small, two-dimensional object using carefully designed metamaterials. The object was wrapped in a cloak that bent light waves around it, effectively making it invisible from certain angles. It wasn't perfect yet. Limitations exist, such as the size of the object that can be cloaked and the range of light wavelengths that the cloak works with, but it was a huge leap forward. But it's not just small objects. Progress is being made toward larger-scale invisibility too. Military applications are one of the biggest driving forces behind this research. Imagine tanks, drones, or even soldiers that can blend seamlessly into their surroundings. Cloaking technologies could revolutionize modern warfare, providing an unmatched level of stealth and surprise. Invisibility technology is also making waves in surveillance. Cameras could become hidden in plain sight. Security systems could blend into the environment, and drones could monitor vast areas without ever being seen. But it's not just about war or spying. There are more peaceful, everyday uses of this technology waiting in the wings. Now let's take a leap forward. What if invisibility became part of everyday life? Imagine driving a car that can become invisible to avoid dangerous situations, or homes with parts that blend into the natural landscape, creating a feeling of living in harmony with nature. Maybe you'll wear an invisibility cloak that lets you walk through crowds unnoticed, perfect for those introverted days. Beyond personal uses, invisibility could also transform architecture. Architects could design buildings that are nearly invisible from certain angles, blending structures into the environment and creating a more harmonious relationship between nature and urban spaces. Cities could become sleek, with towers that fade into the sky, reducing their visual impact while still serving their purpose. But it's not just about aesthetic beauty. Invisibility technology could be used in medicine. Invisible tools could allow surgeons to see more clearly as they operate, reducing the need for large invasive equipment. Emergency workers could use it to search and rescue in dangerous environments, moving unseen to avoid escalating volatile situations. Invisibility could become more than just a trick of the eye. It could become a fundamental part of how we interact with the world. As exciting as invisibility sounds, there are still major challenges standing in the way. One of the biggest hurdles is energy. Cloaking objects requires a tremendous amount of energy to bend light in just the right way. For large objects, the energy demands become even more daunting. How do you create a device that bends light around a car, a building, or even a human without draining vast amounts of power? The solution isn't clear yet. Another challenge is that invisibility cloaks often only work for specific wavelengths of light. Most cloaks developed today are only effective in the microwave or infrared spectrum, meaning they wouldn't work for visible light, which is what the human eye detects. The future of cloaking will depend on developing materials that can manipulate all wavelengths of light, from microwaves to visible light to ultraviolet radiation, so that objects appear completely invisible to human observers. But perhaps the most important challenge is the ethical implications. Imagine a world where anyone or anything could become invisible. How would we protect privacy? What safeguards could be put in place to prevent misuse of this technology? Could invisible drones or cameras infringe on personal freedoms? These are difficult questions that society will need to grapple with as cloaking technology becomes more advanced. The line between privacy and surveillance, protection and manipulation will blur. As with any new technology, the future of invisibility will depend on how we choose to use it. Will it become a tool for good, or will it bring unforeseen consequences? Invisibility might still be in its early stages, but with each passing year, the dream of becoming unseen grows closer to reality. Metamaterials, optical physics, and the brilliant minds behind these advances are pushing the boundaries of what's possible. One day, invisibility may be just another tool in our technological arsenal, a practical, everyday part of life. But as we step into this new world of invisibility, we must remember with great power comes great responsibility. The future of invisibility is full of potential, but also full of choices. And those choices will define how we use this once impossible technology. Imagine standing in your living room and with the press of a button, you instantly find yourself on a tropical beach halfway across the world. No planes, no cars, no time spent in transit, just you disappearing from one place and reappearing in another. Teleportation has long been one of humanity's wildest dreams. But how close are we to turning that dream into reality? In today's world, teleportation remains a staple of science fiction, a dazzling concept we've seen in shows like Star Trek and movies where characters vanish from one place only to appear in another. But behind the fantasy, there's real science at play. Quantum teleportation is already happening in labs around the world. Let's explore how close we are to making teleportation a reality and what's stopping us from teleporting not just information but entire people. First things first, quantum teleportation isn't what you think it is. We're not yet teleporting people or even objects, but what scientists are doing is almost as amazing. They're teleporting information. Teleportation at the quantum level happens thanks to a phenomenon called quantum entanglement. This is when two particles become so deeply connected that the state of one particle can instantly influence the state of another, no matter how far apart they are. Einstein famously called this spooky action at a distance, and today scientists are using this strange property to teleport quantum information across great distances. So how does this relate to teleportation? In quantum teleportation, the quantum state of one particle is transferred to another, using entanglement as the medium. Imagine you have two entangled particles, one with you and the other on a space station orbiting Earth. By manipulating the particle in your lab, you can instantly affect its entangled partner on the space station, effectively teleporting the state from Earth to space without sending any physical matter. This is already happening. In 2017, Chinese scientists made headlines by teleporting quantum information from Earth to a satellite over 1,200 kilometers away, proving that quantum teleportation is real. But let's be clear, we're teleporting information, not matter, not people, just yet. If you're a fan of science fiction, teleportation means stepping onto a platform, pressing a button, and whoosh, you're standing somewhere else entirely. But teleporting people or objects isn't as easy as beaming particles through quantum entanglement. The idea of physically disassembling and then reassembling a human being somewhere else is where science begins to break down. In the world of quantum teleportation, only information is transferred, not the physical object. In Star Trek, the transporter beam breaks down every atom of a person's body and rebuilds them in a new location. In reality, this level of physical teleportation presents a challenge beyond anything we can currently manage. Why? Because every single atom and particle in your body would need to be scanned, transmitted, and reconstructed exactly as it was. Miss a few atoms or get the quantum state wrong, and the person who comes out the other end might not survive the trip, if they appear at all. While science fiction shows this happening seamlessly, the real-world barriers are incredible. We can barely teleport quantum states across a laboratory, let alone recreate something as complex as a human being. If teleporting a person sounds hard, wait until you hear about the energy and data requirements. For teleportation to work, you wouldn't just need to scan every atom, you'd also need to store that information and transmit it. And that takes an almost unimaginable amount of data. To teleport a single human being, you'd need to record the exact position and state of each atom. According to some estimates, the data required to fully describe a person could be around 2.6 times 10 to the power of 42 bits. That's more information than every computer and data center on Earth could store combined. And once you've stored all that information, you still need to transmit it. Even if you could somehow scan, store, and transmit this data, you'd need an enormous amount of energy to break down and reconstruct the atoms. The sheer power required would be astronomical, far more than anything we can generate today. So while we can teleport the quantum states of particles, teleporting entire people remains an energy nightmare. Teleporting humans may seem impossible right now, but the obstacles aren't just about energy or data. There's a deeper, more fundamental challenge that physicists face when trying to scale up quantum teleportation, the very nature of quantum mechanics. At the quantum level, things behave differently than they do in the world we experience every day. Quantum states are fragile. They can be easily disturbed by outside forces. When teleporting quantum information, any interference can cause decoherence, which means the information becomes scrambled and useless. Scaling up teleportation from single particles to entire objects introduces new levels of complexity. In the world of large-scale teleportation, noise, heat, and imperfections would wreak havoc on any attempt to teleport complex structures like objects or people. In quantum experiments, scientists go to great lengths to isolate particles in controlled environments, often cooling them to near absolute zero to prevent any unwanted interactions. But how do you shield an entire person from interference? Even if we solved all these problems, the energy, the data, the quantum fragility, there's still a philosophical question. Would the person who appears at the other end really be the same person? If teleportation involves disassembling and reconstructing you atom by atom, are you still you when you arrive? Or have we created an identical copy while the original you is lost in the process? Teleportation remains one of humanity's greatest dreams. While we're making incredible strides in quantum teleportation, transferring information instantly across great distances, the reality of teleporting people or objects still lies far beyond our current capabilities. The challenges of energy, data, and quantum coherence are monumental, but science is always evolving. One day, we might find a way to overcome these hurdles. Maybe it won't happen tomorrow, or even in the next 100 years. But the pursuit of breaking the barriers of space will continue. And just like the heavier-than-air flight once seemed impossible, teleportation may one day leave the realm of fiction and become part of our reality. Imagine a world where invisible force fields can protect you from danger, a shield that blocks bullets, prevents harm during space travel, and provides security for entire cities. For decades, we've seen force fields in science fiction, from Star Wars to Marvel's Avengers, where these invisible barriers save the day. But is the concept of force fields just a fantastical dream, or is it rooted in real science? It turns out scientists and engineers are already hard at work trying to make force fields a reality. While we're not quite at the level of creating invisible shields that can stop anything, electromagnetic and plasma fields are offering glimpses into a future where force fields might protect us from more than we ever thought possible. The closest thing we have to a force field today involves the use of electromagnetic fields and plasma technology. These fields work by manipulating electrically charged particles, creating an invisible barrier that can contain energy, gas, or even deflect certain types of radiation. In labs across the world, scientists are using magnetic confinement to trap and contain superheated plasma. Plasma, the fourth state of matter, is an incredibly hot gas where the atoms are stripped of their electrons, creating charged particles. This super-hot plasma is difficult to control, but with magnetic fields we can trap and shape it. One of the most famous examples of this technology is the tokamak, a device used in fusion research to contain plasma. By using incredibly strong magnetic fields, these machines hold plasma in place long enough for scientists to study it and even attempt to harness the energy within. So how does this relate to force fields? The ability to confine plasma with magnetic fields is the first step toward creating shields that could one day protect objects from external forces. Right now, these fields are used to control plasma for energy research, but the principles are the same: contain, deflect, and protect. If we can improve the power and stability of these fields, we might be on the verge of a whole new way of shielding ourselves from danger. The next question is, how could a force field protect against solid objects? In science fiction, force fields are often shown as invisible barriers that stop anything from bullets to space debris. But in the real world, creating a barrier that can stop solid matter is far more complicated. In theory, a plasma shield combined with a magnetic field could deflect small objects like charged particles or debris in space. This works because charged particles interact with electromagnetic fields, and by manipulating these fields we can push these particles away. But stopping something like a solid object, a physical bullet or asteroid, would require a much stronger force. To protect against solid objects, a force field would need to exert a strong repelling force on the incoming matter. This could be done using magnetic repulsion if the object is made of metal or contains magnetic properties. For non-magnetic objects, however, the challenge is much harder. Current materials science has yet to find a way to create fields that interact with all types of matter in the way that sci-fi shows imagine. Despite the challenges, force fields could one day change the way we think about defense, space travel, and even personal protection. Imagine a future where soldiers are protected by invisible shields that deflect bullets, vehicles are covered in energy fields that absorb impacts, and spacecraft are safeguarded from dangerous cosmic radiation. One of the most exciting areas for force field development is space travel. Space is a dangerous place filled with micrometeoroids, solar radiation, and cosmic rays that can damage spacecraft and harm astronauts. A force field could act as a protective barrier, shielding spacecraft from this debris and radiation, making long-term space missions much safer. In the military, force fields could become a game-changer in defense. Imagine tanks, ships, or even entire bases protected by invisible shields that could absorb or deflect attacks, giving soldiers an unprecedented level of protection on the battlefield. On a smaller scale, personal shields could protect individuals in dangerous environments, providing a lightweight, portable defense against harm. And beyond defense, think about how force fields could be used in everyday life, protecting homes from natural disasters, or even creating safe spaces in areas with toxic or hazardous environments. The possibilities are endless. But before we get there, we have some serious challenges to overcome. As promising as force fields sound, there are still significant challenges preventing us from creating the sci-fi shields we dream of. One of the biggest hurdles is power generation. Creating and maintaining an electromagnetic or plasma field requires an immense amount of energy, far more than we can generate efficiently today. For a force field to be useful in everyday life or military applications, it would need to be sustainable, able to run on relatively low power while remaining stable for long periods of time. Right now, the amount of energy required to maintain a plasma field is enormous, and scaling this up to protect entire buildings, vehicles, or people is beyond our current technology. Another challenge is stability. Plasma and electromagnetic fields are notoriously difficult to control. In fusion reactors, scientists work tirelessly to keep the plasma contained, and even slight fluctuations can cause the entire field to collapse. Creating a stable, portable force field that can withstand real-world conditions like Earth's atmosphere, temperature changes, and outside interference remains a huge technical challenge. And let's not forget about practicality. Even if we could overcome the energy and stability issues, how practical would it be to deploy force fields in everyday settings? Can we develop the technology to make force fields lightweight, mobile, and easy to produce? Or will they remain limited to high-tech laboratories and specific military applications? The dream of force fields, once thought to be pure science fiction, is slowly moving toward reality. Through the advancements in electromagnetic fields, plasma technology, and materials science, we are beginning to understand how we might one day protect ourselves with invisible shields. But the journey is far from over. As we continue to push the boundaries of science and technology, the challenges of power generation, stability, and practicality will need to be solved. It may take decades, but the idea of force fields is no longer just a fantasy. It's a challenge waiting to be overcome. Imagine you're sitting in a spaceship, staring out at the stars. With a push of a button, the stars suddenly stretch into long beams of light, and in an instant, you're traveling faster than the speed of light. Faster than anything in the universe. It's the kind of thing we've all dreamed of, right? getting to distant galaxies in minutes, not millennia. But here's the thing, Einstein's theory of relativity says that traveling faster than light should be impossible. So is this dream just a fantasy? Or could we one day find a way to break the cosmic speed limit? Let's dive into the world of faster-than-light travel, where the line between science and science fiction blurs. We'll explore the incredible possibilities of warp drives and wormholes, the challenges standing in our way, and what it would mean for our understanding of the universe if we could truly move faster than light. Let's start with a basic question. Why can't we travel faster than light? To answer that, we need to go back to Albert Einstein. His theory of special relativity, published over 100 years ago, laid down a simple but profound rule. Nothing can move faster than light. Why? Because the speed of light, 299,792 kilometers per second, isn't just a speed, it's the speed limit of the universe. If you tried to go faster, strange things would start to happen. The closer you get to the speed of light, the more time slows down for you and the more mass you gain. If you actually hit the speed of light, your mass would become infinite, and you'd need infinite energy to keep going. That's why, as far as we know, nothing with mass can travel faster than light. But what if there was a loophole in these laws, a way to cheat the system, to get around the speed limit without actually breaking it? This is where the ideas of warp drives and wormholes come in, two of the wildest, most exciting concepts in theoretical physics. Now, this is where things get really interesting. Imagine if you didn't have to move through space at all. What if you could bend space around you? That's the idea behind the warp drive, a concept first proposed by physicist Miguel Alcubierre in 1994. In theory, a warp drive doesn't move the ship through space. Instead, it warps the space around the ship. You'd compress space in front of you and expand it behind you, effectively surfing a wave of space-time. The beauty of this idea is that you're not breaking the speed of light. You're bending the very fabric of the universe itself. The spaceship inside the warp bubble would still be stationary relative to the space around it, but the bubble itself could move faster than light. But there's another way to beat the speed of light wormholes. These are like shortcuts through space-time. Imagine a tunnel connecting two distant parts of the universe. Instead of traveling across the universe, you'd travel through it, arriving at your destination almost instantly. Wormholes are predicted by Einstein's general theory of relativity, and if we could create a stable one, it might allow faster-than-light travel without ever violating the speed limit. Both warp drives and wormholes offer tantalizing possibilities, but as exciting as these ideas are, there's one big problem. We haven't figured out how to make them work yet. As cool as warp drives and wormholes sound, the challenges to making them real are mind-blowing. For starters, a warp drive would need an insane amount of energy, far more than we could generate with today's technology. Some estimates suggest that powering a warp drive could require the energy of an entire star or more. And it's not just any energy. Negative energy or exotic matter is needed, and we're still not sure if such things even exist in the quantities we'd need. And then there's the issue of wormholes. Theoretically, wormholes could connect distant points in the universe, but wormholes are unstable. They would collapse before you could ever travel through them. To keep a wormhole open, you'd need exotic matter with negative energy, something we've never observed in nature. Even if we could solve the energy and stability issues, there are deeper problems. Time travel paradoxes could arise with faster-than-light travel. Moving faster than light could allow you to arrive at a destination before you even left, potentially creating causality violations, in other words, messing with the fabric of time itself. If you could go back in time and change events, you'd run into the famous grandfather paradox, where you might prevent your own existence. This isn't just a thought experiment. Causality is a fundamental part of our universe, and faster-than-light travel might break it. Despite these challenges, researchers are making small but meaningful breakthroughs in our understanding of space-time. While warp drives and wormholes may seem like far future concepts, scientists are experimenting with new ways to manipulate gravity and space-time. One promising area is the study of gravitational waves, ripples in space-time caused by massive objects like black holes. By understanding how space-time behaves on a fundamental level, we're getting closer to the possibility of bending it to our will. And who knows? Maybe one day we'll crack the code of how to create a real warp drive or stabilize a wormhole. If faster-than-light travel ever becomes possible, it wouldn't just change how we explore the universe, it would change everything we know about reality. Causality, the very fabric of time and space, might unravel. The boundaries between past, present and future could blur. Entire civilizations could communicate or travel instantly across galaxies, making distances that seem insurmountable today feel trivial. Faster-than-light travel would force us to rethink our place in the universe. Suddenly the cosmos wouldn't seem so vast and lonely. We could visit planets around distant stars, explore new worlds, and maybe even discover alien civilizations. But with great power comes great responsibility. What would it mean for our identity, for free will, if we could move through time and space in ways we never thought possible? Faster-than-light travel remains one of humanity's greatest dreams. While the challenges are enormous, energy, exotic matter, and the fabric of causality itself, it's not beyond the realm of possibility. As our understanding of space-time grows, we're inching closer to unlocking the secrets of the universe. One day, what seems impossible today might become reality, and the cosmic speed limit might just be another barrier waiting to be broken. Imagine with the flip of a switch, you travel to the future, where entire civilizations have risen and fallen. Or perhaps you step through a portal and find yourself standing in the past, witnessing moments that shaped history. Time travel, a concept that has fascinated us for centuries, has been a key theme in everything from ancient myths to modern science fiction. But what does science say about time travel? Could we ever manipulate time like we do space? While it may seem like fantasy, Einstein's theory of relativity showed us that time is far more flexible than we once thought. We'll dive into the intriguing world of time travel, exploring time dilation, closed time-like curves, paradoxes, and the mind-bending possibilities of quantum mechanics. This journey will challenge everything you think you know about time. Let's start with a concept that's not science fiction. It's science fact. Thanks to Einstein's theory of relativity, we know that time doesn't flow at the same speed for everyone. In fact, the faster you move, the more time slows down for you. This is called time dilation, and it's been proven over and over again with experiments. Astronauts, for instance, experience time slightly slower than we do on Earth because they're moving so fast in space. Here's how it works. As you approach the speed of light, time starts to stretch. The closer you get, the more pronounced the effect. If you were able to travel at, say, 99.9% of the speed of light, time would slow down dramatically for you compared to everyone back on Earth. A year on your spaceship might pass, but when you return, you could find that decades or even centuries have passed on Earth. This is the key to future travel. In theory, by traveling close to the speed of light, we could leap far into the future, witnessing events and technologies we can only dream about today. But while traveling to the future may be possible, traveling to the past is where things get really strange. Now let's talk about traveling to the past. In Einstein's theory of general relativity, there are certain conditions, extreme ones, where time could loop back on itself. These loops are called closed time-like curves, or CTCs. One of the most intriguing possibilities for creating a CTC involves black holes and wormholes. If you're orbiting a black hole, a place where gravity is so strong that even light can't escape, near the event horizon, time starts to warp and bend in strange ways. Theoretically, under the right conditions, a wormhole, a shortcut through space-time, could open up, connecting two distant points in space and time. If you step into one end of the wormhole, you could emerge at the other end in the past, potentially traveling back to an earlier moment in time. Wormholes and black holes give us a tantalizing glimpse into the possibility of time travel to the past. But there's one big problem. We've never observed a stable wormhole, and creating one would likely require an exotic form of matter with negative energy, something we've never been able to produce in large quantities. While closed time-like curves are theoretically possible, the idea of traveling back in time raises serious questions, ones that challenge the very nature of reality. What happens if you go back and change something? Could you alter the course of history? Or would the universe find a way to protect itself from paradoxes? This brings us to one of the biggest headaches in time travel, the grandfather paradox. Imagine you go back in time and accidentally prevent your grandfather from meeting your grandmother. If they never meet, they never have your parent, and you're never born. But if you're never born, how did you go back in time to prevent them from meeting in the first place? This logical puzzle is at the heart of the time travel paradox. If changing the past can alter the future, it seems like time travel could break the fabric of cause and effect, something fundamental to our understanding of the universe. Some scientists suggest that even if time travel to the past were possible, the universe might self-correct, ensuring that any changes you make wouldn't alter the timeline in a major way. This is called the Novikov self-consistency principle, which states that the events in time are consistent. That is, you can't create paradoxes, because time itself will prevent them from happening. In this view, you could go back in time, but anything you do would already be part of history. Others, however, think that time travel could lead to the creation of multiple timelines, with each change branching off into a parallel universe. In one timeline, you prevent your grandfather from meeting your grandmother, but in another, everything plays out as it originally did. This idea of multiverse time travel opens up a whole new level of complexity. But what if the rules of time travel are different at the quantum level? Quantum mechanics, the science of the very small, opens up a whole new set of possibilities. In the quantum world, particles can exist in multiple states at once, and information can travel in ways that seem to violate the normal rules of time. One of the most intriguing ideas is the possibility of quantum time loops, where a particle can, in a sense, interact with its own past. While this might seem like science fiction, certain interpretations of quantum mechanics suggest that time loops could exist at the smallest scales. Some researchers have even proposed that time travel might be possible in the quantum realm, where paradoxes are avoided because quantum systems can be in multiple states at the same time. Could these quantum effects scale up to allow time travel for humans? That's still unknown, but it's a fascinating area of research. Quantum mechanics has already proven that the universe behaves in ways that defy common sense, so who's to say what's truly possible when it comes to time? But even if we could travel through time, should we? The ethical concerns surrounding time travel are enormous. What would happen if people could freely move through time, changing events to suit their needs? What if governments or individuals used time travel as a tool for power, altering history for their own gain? Time travel could lead to unintended consequences, from the collapse of entire civilizations to the erasure of personal memories and experiences. Imagine living in a world where the past is constantly being rewritten, where the events that shaped your life could vanish in an instant. The potential for misuse is staggering. That's why many scientists argue that even if time travel were possible, it would need to be strictly regulated, with safeguards in place to prevent chaos. But enforcing those rules would be incredibly difficult. After all, how do you police something that exists outside of time? Time travel is one of the most tempting ideas in all of science. The ability to leap forward into the future or go back and relive the past is something we've all imagined. But as we've seen, the reality of time travel is filled with paradoxes, challenges, and ethical concerns. While Einstein's relativity and quantum mechanics offer us a glimpse into the possibility of bending time, the consequences of doing so could be more than we can handle. As we continue to explore the mysteries of time, we must ask ourselves, is the ability to manipulate time worth the risk? Or is time travel a door that's better left unopened? What would happen if you made a different choice in life? What if you turned left instead of right? What if you took that job offer or moved to a different city? Now, imagine that for every decision you've ever made, a new universe was created, one where the version of you made the opposite choice. This is the concept of the multiverse, where the idea of parallel universes suggests that for every possible outcome, there's a reality where it happens. It's a theory that stretches the limits of our imagination, but it's also grounded in physics we know today. From the many worlds interpretation of quantum mechanics to the idea of eternal inflation, scientists are exploring the idea that our universe might just be one of infinite realities. Let's discuss the world of parallel universes and see how these theories could change everything we think we know about existence, free will, and who we are. To understand how parallel universes might work, we need to start with quantum mechanics. In the quantum world, particles don't behave the way we expect. Instead of being in one place at one time, a particle can exist in multiple states simultaneously, a phenomenon called superposition. According to the many worlds interpretation of quantum mechanics, every time a quantum event occurs, say, a particle takes one path instead of another, the universe splits into two. One universe represents the reality where the particle took the first path, and the other represents the reality where it took the second. This means that with every quantum event, a new universe is created. In this interpretation, every possible outcome of every event in the universe creates a new universe. Did you take the bus today or drive? In one universe you took the bus, in another you drove. These small decisions might seem insignificant, but over time, the number of universes grows exponentially, creating a multiverse of infinite possibilities. The many worlds interpretation suggests that all these parallel universes are equally real, and while we can only experience one, there are countless versions of ourselves out there living out different lives. But parallel universes aren't just confined to the quantum world. In cosmology, the study of the universe as a whole, there's another theory that points to the existence of a multiverse eternal inflation. According to inflation theory, shortly after the Big Bang, the universe underwent a period of rapid expansion, or inflation, where space itself stretched faster than the speed of light. This inflation didn't happen uniformly. Tiny quantum fluctuations caused pockets of space to stop inflating while others continued. This results in bubble universes, each one with its own distinct properties, laws of physics, and even dimensions. This means that our universe, the one we live in, could just be one of many. Each of these bubble universes exists within a larger multiverse, and while we may never see them, they're out there, expanding and evolving just like ours. In some universes, the laws of physics might be slightly different. In others, entire galaxies might look completely alien. The multiverse could be filled with realities so strange and different that they challenge everything we think we know. But here's the big question. Can we access these parallel universes? Is there a way to interact with or even travel to them? Theoretically, there are some frameworks that suggest it might be possible. Wormholes, for instance, could, in theory, connect one part of the universe to another. Some researchers speculate that wormholes could also connect different universes within the multiverse. By traveling through one of these cosmic bridges, we could potentially enter a parallel reality. Another possibility comes from the study of quantum entanglement. In the quantum world, particles can become entangled, meaning that the state of one particle is instantly connected to the state of another, even if they're light years apart. Some physicists believe that entanglement might provide a clue about how parallel universes interact. While we don't have any practical way to explore this yet, it's an area of research that could one day open the door to traveling between universes. But even if we can't travel to parallel universes, the mere idea that they exist is enough to change the way we think about reality. The existence of the multiverse doesn't just raise scientific questions, it forces us to rethink who we are and what reality means. If there are countless versions of us living out different lives in parallel universes, what does that say about free will? Are our choices truly our own, or are they just one of many possibilities that play out across different realities? The multiverse also challenges our understanding of identity. If there are infinite versions of you, each one making different choices and experiencing different outcomes, which version is the real you? Are we just one of many, or is there something unique about the version of ourselves that we experience? And then there's the question of existence itself. If our universe is just one of many, it forces us to ask, why this universe? Why are we here, in this reality, rather than any of the countless others? Are we special, or is our existence just one possibility among infinite others? The idea of a multiverse is both thrilling and unsettling. It opens up a universe, or should I say universes, of possibilities. In one reality, we may be exploring distant galaxies. In another, we may never have left Earth. The multiverse forces us to confront deep questions about our place in the cosmos, our choices, and the nature of reality itself. As we continue to explore the mysteries of quantum mechanics and cosmology, we may one day unlock the secrets of the multiverse. And who knows? The reality we experience now might just be the beginning of something much, much bigger. Imagine a machine that runs forever. No need for fuel, no loss of power, no winding down, just pure, endless energy, spinning on and on for eternity. It sounds like the answer to all of humanity's problems, a source of limitless energy. This is the dream of the Perpetual motion machine, a device that, once started, would never stop. For centuries, inventors and dreamers have chased this impossible dream. But there's one major obstacle standing in their way: the laws of physics. Specifically, the laws of thermodynamics tell us that perpetual motion, while fascinating, is fundamentally impossible. So why can't we build a machine that runs forever? Let's dive into the science behind perpetual motion, explore the laws of thermodynamics, and look at some of the most famous historical attempts to break the rules. And just for fun, we'll take a peek at the exotic ideas like vacuum energy and zero-point energy that some believe might one day let us cheat the system. To understand why a perpetual motion machine is impossible, we need to talk about the laws of thermodynamics, the rules that govern energy in our universe. These laws are the reason why, no matter how clever or creative we are, energy can't be created out of nothing, and no machine can run without eventually winding down. The first law of thermodynamics is pretty straightforward. It's the law of energy conservation. It tells us that energy can't be created or destroyed. It can only be transferred or converted from one form to another. So, for a machine to keep running, it needs a constant input of energy. No input, no motion. Then there's the second law of thermodynamics, which is where things get even trickier. This law deals with entropy, which is a fancy word for disorder. It tells us that in any energy transfer or conversion, some energy is always lost to heat. This means no process is 100% efficient. Over time, energy will dissipate and the system will slow down and stop. So, when you hear people talk about building a machine that runs forever, remember, it would have to violate one or both of these fundamental laws. A perpetual motion machine would need to create energy out of nothing, or somehow avoid the inevitable loss of energy to entropy. And according to our current understanding of physics, that's just not possible. But that hasn't stopped people from trying. Throughout history, countless inventors have attempted to defy the laws of thermodynamics by creating perpetual motion machines. Some believed they were on the verge of the greatest discovery in human history, an invention that would revolutionize energy forever. But as promising as these machines might have looked, they all failed in the end. One of the earliest examples comes from the 13th century, when a Bharatiya scholar named Bhaskara designed a wheel that was supposed to spin forever. His idea: a wheel with weights attached to the spokes, shifting as the wheel turned, providing continuous motion. It seemed simple, but no matter how many times inventors tried to tweak and improve the design, the machine eventually came to a stop. In the 18th century, a German mathematician named Johann Bessler claimed he had built a perpetual motion machine that could turn indefinitely. He guarded the secret of his design fiercely, but after he died, no one was able to reproduce his machine. While Bessler's invention stirred curiosity, it eventually faded into history as another failed attempt. One of the most famous examples is the overbalanced wheel, an idea that many inventors tried over the years. These machines relied on the idea that weights could shift as the wheel turned, causing it to keep spinning forever. But as elegant as they might have looked, the friction and energy loss eventually brought them to a standstill, just like all the others. These historical attempts are a testament to human ingenuity and determination. But they also remind us of the limits imposed by the fundamental laws of nature. As long as we are bound by thermodynamics, perpetual motion will remain an elusive dream. But that hasn't stopped people from speculating. Could there be some exotic loophole in the laws of physics that might one day allow us to build a machine that never stops? Let's take a look at the wildest ideas out there. While the laws of thermodynamics seem ironclad, some scientists and theorists have wondered if there might be a way to tap into exotic forms of energy, sources that don't play by the usual rules. One of the most exciting ideas in this area is something called vacuum energy. In quantum physics, a vacuum isn't really empty. Instead, it's filled with tiny, fluctuating particles that pop in and out of existence. This is known as vacuum energy, and some believe it could hold the key to unlocking new forms of power. Theoretically, if we could harness this energy, we might be able to create a system that generates power indefinitely, a kind of quantum, perpetual motion machine. Another idea is zero-point energy, the lowest possible energy that a quantum system can have. Even at absolute zero, where all motion stops, quantum systems still retain a small amount of energy. Some have speculated that if we could tap into this zero-point energy, we might have access to a limitless power source. Sounds incredible, right? But the problem is, while these concepts are fascinating, we have no practical way to extract and use this energy on a large scale. Even if vacuum energy or zero-point energy exists in measurable quantities, it's locked away in a form that's incredibly difficult to harness. So, while these ideas are tempting, they don't allow us to break the laws of thermodynamics. The dream of perpetual motion lives on in our imaginations and in speculative physics. But for now, the laws of thermodynamics remain unbroken, and the quest for endless energy remains just that, a quest. The idea of a machine that runs forever, a machine that creates energy without needing any input, is one of the most captivating dreams in human history. But as long as the laws of thermodynamics govern our universe, it seems that perpetual motion will remain an impossibility. Still, the efforts of those who tried and failed remind us of the boundless curiosity and creativity that drives us forward. And who knows? Perhaps in the distant future, we'll discover some new understanding of the universe that allows us to tap into exotic energy sources and change the rules of physics. Until then, the perpetual motion machine remains a symbol of our endless pursuit of the impossible. Every day, we feel its pull, the invisible force that holds us to the ground, keeps the planets in orbit, and shapes the very structure of the universe, gravity. It's everywhere, and we've spent centuries trying to understand and overcome it. What if we could? What if we could create anti-gravity, a technology that frees us from gravity's grasp, allowing us to float, fly and explore the stars without the heavy cost of rockets and fuel? The idea of anti-gravity has captured our imaginations for generations, from science fiction to real-world research. But here's the question: can we ever overcome gravity? Could we one day bend or even cancel out gravity like we do with other forces? To answer that, we'll need to dive into Einstein's theory of general relativity, explore speculative ideas about gravity modification, and see how close or far we are from realizing the dream of anti-gravity. Before we talk about how we might overcome gravity, we need to understand what gravity is. For a long time, we thought of gravity as a simple force, like magnetism or electricity, that pulls objects toward each other. But in 1915, Albert Einstein changed everything with his theory of general relativity. According to Einstein, gravity isn't a force in the traditional sense. Instead, it's the result of the warping of space-time. Massive objects like planets and stars bend the fabric of space-time around them, and what we experience as gravity is just objects following the curves in that fabric. In other words, gravity is all about geometry. The more massive the object, the deeper the curve it creates in space-time, and the stronger its gravitational pull. This idea revolutionized our understanding of the universe, but it also makes the idea of anti-gravity a lot more complicated. If gravity is the warping of space-time, how do you create a technology that cancels or reverses that warping? So, can we create anti-gravity? In theory, there are a few speculative concepts that might help us bend or negate gravity. One idea is the existence of a particle called the graviton. Just like light is made of photons, some physicists believe that gravity might be carried by gravitons, hypothetical particles that transmit the force of gravity at the quantum level. If we could detect or manipulate gravitons, we might be able to influence gravity in ways we've never imagined. But we've never actually observed a graviton. It's purely theoretical, and detecting these particles, if they exist, would be incredibly difficult. Another speculative idea involves antimatter. Antimatter is like regular matter, but with opposite properties. When antimatter comes into contact with matter, the two annihilate each other in a burst of energy. Some have speculated that antimatter could have anti-gravity properties, repelling rather than attracting. But experiments so far have shown that antimatter seems to behave just like regular matter when it comes to gravity. There are also theories involving exotic particles and negative energy. For example, some physicists suggest that certain exotic particles, if they exist, could bend space-time in ways that reverse the effects of gravity. Others look to negative energy as a way to create repulsive forces that counteract gravity. While these ideas are fascinating, they remain purely speculative. We've yet to discover a reliable method for generating anti-gravity. But that hasn't stopped scientists from trying. So, what about real-world research? Are there any efforts today to modify or control gravity? While we're far from building anti-gravity devices like you see in science fiction, there are some exciting developments in the field of gravity research. One area of focus is gravity modification through the study of superconductors. Some experiments suggest that superconducting materials, when cooled to extremely low temperatures, can interact with gravitational fields in unusual ways. While these effects are tiny and hard to measure, they hint at the possibility of manipulating gravity on a small scale. Another promising area of research involves quantum gravity, the study of how gravity behaves at the smallest scales. While general relativity explains gravity on a large scale, it doesn't work well at the quantum level. By exploring the connection between quantum mechanics and gravity, researchers hope to uncover new insights that could one day lead to breakthroughs in gravity control. Some researchers are even exploring the possibility of using artificial gravity in space. While this isn't the same as anti-gravity, it's a step towards controlling gravity for practical purposes, like creating environments where astronauts can live and work without the negative effects of weightlessness. As exciting as these speculative ideas and research efforts are, we have to face the reality that anti-gravity, as imagined in science fiction, may be impossible. The problem isn't just technological, it's theoretical. The very nature of gravity, as described by general relativity, makes it incredibly difficult to overcome. Remember, gravity isn't a force like magnetism that we can simply repel or block. It's the curvature of space-time itself, caused by the presence of mass. To create true anti-gravity, we would need to figure out a way to flatten or reverse the curvature of space-time. A feat that, at least with our current understanding of physics, seems unattainable. Even if we could create negative energy or discover exotic particles, The amount of energy required to significantly warp space-time in the opposite direction, enough to create anti-gravity, would be astronomical. In the end, we might find that gravity is simply a fundamental part of the structure of the universe, one that we can't easily escape. The idea of anti-gravity remains one of the most captivating dreams in science. From Einstein's relativity to the speculative world of gravitons and quantum gravity, we're constantly pushing the boundaries of what we know about the universe. While true anti-gravity may still be out of reach, the research into gravity modification and quantum phenomena gives us hope that one day we might unlock the secrets of controlling gravity. For now, though gravity holds firm as one of the fundamental forces of the universe, binding us to the Earth and the stars. What if we could tap into an energy source so powerful that it would never run out? One that could power cities, vehicles and space exploration for generations. It's the holy grail of energy research, the quest for infinite energy, from the core of the sun, where fusion burns endlessly, to the mysterious world of zero-point energy at the quantum level. Scientists have long searched for ways to unlock the boundless energy of the universe. But are we any closer to achieving limitless power? Can we harness the energy of stars or extract cosmic power from black holes? Now we'll explore the infinite energy sources where the promise of endless power meets the limits of physics. Let's start with the most promising candidate for infinite energy fusion power. Fusion is the same process that powers the sun and all the stars in the universe. At its core, fusion takes light elements, like hydrogen, and forces them together to form heavier elements, releasing enormous amounts of energy in the process. Unlike fission, which splits atoms apart and produces dangerous radioactive waste, fusion is clean, safe, and nearly limitless, because the fuel for fusion, hydrogen, is abundant throughout the universe. If we could master fusion power here on Earth, it could provide us with a virtually endless supply of energy. The benefits of fusion are incredible. It's not just clean energy, it's also incredibly efficient. A small amount of fusion fuel can produce more energy than tons of coal or oil. No carbon emissions, no long-lived radioactive waste. It's the perfect energy source for a planet that's facing both energy demands and environmental challenges. So, why aren't we using fusion power yet? Well, that's because while fusion happens naturally in stars, replicating that process on Earth is incredibly difficult. To make fusion happen, you need to create conditions similar to the core of the sun, temperatures of millions of degrees, and enough pressure to force hydrogen atoms to collide and fuse. This requires massive magnetic fields and advanced technology to contain the plasma, the superheated gas where fusion occurs. The biggest challenge is maintaining these conditions long enough to achieve sustained fusion, fusion that produces more energy than it consumes. We've had success with short bursts of fusion, but keeping it going long enough to power the grid is the next frontier. The dream of fusion power is tantalizingly close, but the technology still has major challenges to overcome. If we crack the code, we could enter a new era of energy production, one where the power of stars is at our fingertips. But until then, fusion remains a challenge that's both inspiring and elusive. Next, we turn to something even more mysterious: zero-point energy. Unlike fusion, which relies on massive amounts of heat and pressure, zero-point energy comes from the quantum world, where the rules of physics start to get strange. Even in the vacuum of space, where there's no matter and no light, nothing, there's still energy. At the quantum level, particles and antiparticles are constantly popping in and out of existence, fluctuating in a seemingly empty vacuum. This is what we call zero-point energy, the lowest possible energy a quantum system can have, even when all other energy is removed. In theory, zero-point energy is everywhere. If we could find a way to extract it, we'd have access to a limitless supply of energy, an energy source that could power our world without ever running out. It's the ultimate dream, an energy source that's abundant, clean, and free. But there's a problem. While zero-point energy exists, figuring out how to harness it is a different story. The challenge with zero-point energy is that even though the vacuum is teeming with tiny fluctuations, these energy bursts are so small and short-lived that we can't capture them in any meaningful way. The technology to extract and store this energy simply doesn't exist and might never exist. Some scientists speculate that the laws of physics might prevent us from ever tapping into zero-point energy on a large scale. The energy may be there, but it's locked away in a form that's nearly impossible to extract. While zero-point energy is a fascinating idea, it remains just that, an idea. The promise of limitless energy from the quantum vacuum is still far beyond our reach. But what about cosmic energy? If we can't harness fusion or zero-point energy just yet, could we turn to the vast resources of the cosmos? One of the most ambitious ideas comes from a concept called the Dyson sphere, an enormous structure that could surround a star and capture all of its energy. Imagine a massive shell or swarm of satellites surrounding a star like our Sun, absorbing its energy output and transferring that power to civilizations across the galaxy. A single Dyson sphere could produce more energy than all of Earth's power plants combined, and it would last as long as the star itself. The energy output of a star is truly staggering. If we could build a Dyson sphere, we'd have access to more energy than we could ever need. It would be the ultimate solution to humanity's energy problems. Limitless power, straight from the heart of a star. But building a Dyson sphere is wildly impractical with our current technology. The amount of material required would be astronomical, and the engineering challenges are mind-boggling. It's an idea that belongs to an advanced civilization, one far beyond where we are today. There's also the idea of harvesting energy from black holes, another cosmic source of immense power. Black holes, with their intense gravitational pull, can generate huge amounts of energy by consuming matter and emitting radiation through processes like Hawking radiation. Some scientists have speculated that, in the distant future, we could place spacecraft near black holes to collect this energy. But the risks are enormous. Getting too close to a black hole could mean being pulled into the event horizon, with no hope of escape. And even if we could safely harvest this energy, the amount of infrastructure and technology required would be beyond anything we currently have. Whether it's a Dyson sphere around a star or energy harvesting from black holes, these ideas are fascinating. But they come with massive physical constraints. The energy is out there, but tapping into it is another story. For now, these remain far-off concepts, more suited to the dreams of future civilizations than to the immediate needs of our world today. The quest for infinite energy has driven scientists and dreamers for centuries, from the fiery heart of the fusion reactor to the mysterious fluctuations of zero-point energy and the ambitious vision of Dyson spheres. While each of these ideas holds immense promise, they also remind us of the limits of our technology. and our understanding of the universe. We've all heard the story. Isaac Newton saw an apple fall from a tree and suddenly understood gravity. This simple moment in history sparked one of the greatest revolutions in science, leading to Newton's laws, rules that would define how we understood the universe for centuries. But Newton's laws, as groundbreaking as they were, didn't last forever. Then came Albert Einstein. With his theory of relativity, Einstein didn't just add a new chapter to Newton's story, he rewrote the book. Einstein showed us that space and time weren't as absolute as Newton once believed. They could bend and warp in response to gravity. It was a paradigm shift, a fundamental change in how we view the universe. And it left us with a tantalizing question: can physics be broken? Is it possible that the laws of physics, which seem so ironclad, might one day be overturned? Could future discoveries rewrite the rules yet again, just like Einstein did with Newton? To answer the question of whether physics can be broken, we need to understand how the field has evolved over time. When Newton developed his laws of motion in the 17th century, they were considered absolute truths, laws that explained everything from how an apple falls to how planets orbit the sun. But then, as we started exploring the cosmos and delving deeper into the nature of light and time, we discovered that Newton's laws didn't always hold up, especially at extreme speeds or in the presence of strong gravitational forces. Then Einstein's theory came along. With his theory of general relativity, Einstein didn't erase Newton's work but expanded on it, giving us a more complete picture of how the universe works. But Einstein's work didn't end the story. In the early 20th century, the discovery of quantum mechanics, the strange, unpredictable behavior of particles at the smallest scales, overturned everything we thought we knew about physics. Suddenly, particles could exist in two places at once, and the very act of observing them could change their behavior. This was a world that Einstein himself struggled to accept. From Newton to Einstein and beyond, the laws of physics have evolved as we've learned more about the universe. Each time we've made a breakthrough, it's not that physics has been broken, but rather that our understanding of it has deepened. So, what about today? Are the rules we live by now truly immutable? Or could the next discovery lead to another scientific revolution? The laws of physics as we know them today are incredibly powerful. They explain everything from the formation of galaxies to the behavior of subatomic particles. But even now there are mysteries, phenomena we don't fully understand, like dark matter, dark energy, or the singularities inside black holes. Could these hold the key to breaking the laws of physics? One thing we've learned from history is that the laws of physics are not as unchangeable as they might seem. Every time we've made a major discovery, it's come from challenging what we thought we knew. When we discovered quantum mechanics, it didn't fit neatly into the framework of relativity. These two pillars of modern physics, relativity and quantum mechanics, work beautifully on their own, but they're incompatible with each other when you try to combine them. So, are the laws of physics truly immutable? The answer might lie in the gaps in our understanding. Physicists today are searching for a unified theory, a theory that combines relativity and quantum mechanics into one comprehensive framework. If we find it, it could rewrite the rules once again. Throughout history, science has been shaped when new discoveries radically changed how we view the world. These moments are called paradigm shifts, where the old way of thinking is replaced by something completely new. Newton's discovery of gravity was one such moment. Einstein's relativity was another. And quantum mechanics? That was yet another revolution. The thing about paradigm shifts is that they don't just add new information, they overturn old assumptions. For example, classical physics assumed that everything could be precisely measured and predicted. But with quantum mechanics, we discovered that at the smallest scales, the universe is inherently uncertain. These revolutions have changed everything. They've expanded our understanding of space, time, and matter, and even redefined what it means to observe the universe. And if history teaches us anything, it's that there will likely be more revolutions to come. What will the next revolution be? Some physicists speculate that we're on the verge of a new paradigm shift, one that could challenge our current understanding of gravity, space-time, or even the fundamental forces of the universe. It might come from the discovery of dark matter, or perhaps from a breakthrough in understanding quantum gravity. Or maybe it'll come from something we can't even imagine yet. After all, Newton couldn't have predicted Einstein, and Einstein couldn't have predicted quantum mechanics. So, can physics be broken? The answer isn't a simple yes or no. The laws of physics as we know them have been remarkably successful at explaining the universe we see. But history shows us that science evolves. What we consider immutable today could be challenged tomorrow by a discovery that shifts our entire understanding of reality. The future holds endless possibilities. As we continue to explore the deepest mysteries of the universe, from black holes to the quantum realm, we may find that the laws of physics are not as fixed as we thought. The rules of today could be the stepping stones to the revolutions of tomorrow. And that's the beauty of science. It's not about knowing everything, but about the endless pursuit of understanding. Imagine a world where the impossible becomes possible. What if we could travel faster than light, bend time to our will, and tap into the infinite energy of the universe? These technologies could transform society in ways we can't fully imagine, erasing borders, ending energy crises, and even allowing us to explore distant galaxies. But there's another side to these extraordinary possibilities, the ethical dilemmas they bring. While these breakthroughs could create a better world, they also have the potential to create unimaginable harm. What are the risks of playing with fundamental forces of nature? How would society change if we broke the very laws that govern the universe? Today, we'll explore the ethical concerns of impossible technologies, asking ourselves whether some impossibilities, if achieved, could be too dangerous to pursue. Let's start with the dream. Imagine a world where we've cracked the secrets of faster-than-light travel, allowing us to explore distant galaxies in mere moments. Perpetual energy sources power entire cities, and time travel lets us peek into the past, or even change it. On the surface, this sounds like a utopia, an era of limitless potential where humanity has transcended the limits of physics. But as with any powerful tool, these technologies come with risks. What happens to the world when distance and time no longer matter? How do we protect ourselves from the unintended consequences of breaking the laws of nature? Would these breakthroughs improve society or tear it apart? When we remove the boundaries of space and time, The consequences ripple across society. Teleportation could erase privacy, as anyone could appear anywhere at any time. Faster than light travel could lead to a race to exploit distant resources, or even weaponize entire planets. And time travel? That could disrupt the flow of history, unraveling the fabric of society as we know it. While these technologies promise to solve many of our problems, they also raise difficult questions about control, security, and ethics. Who gets to decide how these technologies are used? And can we trust that these powers won't be abused? Take, for example, the idea of time travel. On the surface, the ability to visit the past sounds like a scientific marvel, but it's fraught with potential for disaster. The power to change history could be devastating. What happens if someone goes back in time and alters a critical event? Could entire civilizations be erased with the flick of a switch? This brings us to the classic dilemma, the grandfather paradox. If you go back in time and prevent your grandparents from meeting, do you even exist? But beyond these paradoxes, time travel introduces real-world ethical concerns. Governments or individuals could manipulate history for their own gain, reshaping the present to suit their interests, or worse, erasing those who stand in their way. Even faster than light travel, something that could revolutionize space exploration, poses risks. Imagine the race to dominate space, a new kind of colonization driven by the desire for power, territory, or resources in distant galaxies. FTL could be weaponized, leading to devastating intergalactic conflicts, where ships could appear without warning to launch attacks on rival planets. The consequences of such power in the wrong hands could be catastrophic. And then there's the possibility of infinite energy through zero-point energy, or fusion power. While these sources could end the world's energy crisis, they could also lead to imbalances of power. Imagine a world where a handful of nations control all the energy, using it to dictate terms to the rest of the world. What happens to equality, justice, and fairness in a world where energy flows freely for some and not for others? These technologies may seem like miracles, but they come with moral risks that could far outweigh the benefits. The more power we unlock, the more responsibility we bear for how it's used. So, could these once impossible breakthroughs create more harm than good? The answer may depend on how we choose to control and regulate them. With great power comes great responsibility. If we unlock technologies that allow us to manipulate time, warp space, or tap into infinite energy, we have a moral obligation to consider the risks and consequences of these actions. We are not just scientists and inventors. We are the guardians of forces that could reshape the universe. The risks of playing with fundamental forces of nature are immense. The pursuit of these impossible technologies may lead us to cross lines we should never cross. Imagine using gravitational manipulation to control entire planets, or bending the fabric of space-time in ways that create unpredictable consequences for future generations. Even in our pursuit of infinite energy, there are risks. Fusion reactors could provide clean, limitless power. But what if something goes wrong? What if a fusion plant meltdown leads to environmental disasters far worse than anything we've seen from fossil fuels or nuclear power? As we push the boundaries of physics, we must ask ourselves, are we prepared for the consequences? And with time travel, we face not just technical challenges, but deep ethical dilemmas. Should we even have the right to change the past? Could altering time itself create irreversible damage to our reality? The temptation to manipulate history is immense, but the costs could be too high. With every step toward the impossible, we walk a fine line between progress and destruction. The fundamental forces of nature aren't just there for us to manipulate, they are the building blocks of reality. And when we tamper with them, we take on a moral responsibility to ensure that the future we create is one of safety, justice, and stability. As we explore the boundaries of the impossible, we are not just pushing the limits of science, we are venturing into unknown moral territory. These technologies, if achieved, could reshape the fabric of society, blurring the lines between what's possible and what's right. And with great power comes the obligation to use it wisely. The future will bring discoveries we can't yet imagine, but it's up to us to ensure that these breakthroughs are used for the greater good. If we ignore the ethical concerns, we risk a future where the promise of impossible technologies turns into a reality we can no longer control. At the edge of what we know, where science meets the unknown, stands a discipline that has always dared to ask the biggest questions: theoretical physics. For centuries, it has been the beating heart of our quest to understand the universe, offering us a glimpse into realms we can't yet observe or experiment with directly. But what makes theoretical physics so important? How does it help us push the boundaries of what we consider possible? Through bold ideas and mathematical elegance, theoretical physics expands the horizon of possibility, allowing us to imagine new worlds, new forces, and even new laws of nature. Now we'll dive into the fascinating world of theoretical physics, exploring how it serves as the bridge between mathematics, experimentation, and technology, and how it drives us to push the limits of science itself. At its core, theoretical physics is about imagination. It's where physicists take the known laws of the universe and ask, what if? What if the universe had more dimensions than we can see? What if time itself can be bent and manipulated? What if particles behave in ways we've never observed? These questions aren't just speculation, they're grounded in the language of mathematics. Theoretical physicists use math to explore ideas that seem impossible, but are consistent with the laws of physics. This is how relativity was born. When Albert Einstein imagined that space and time were linked, he used mathematics to show that this wasn't just an idea, but a physical reality. The same goes for quantum mechanics, which started as mathematical insights into how particles behave, even though they defy common sense. In this way, theoretical physics expands the limits of what we believe is possible. It opens up entire new fields of study by challenging the assumptions we make about the universe. Einstein's theories of relativity completely redefined our understanding of space and time, showing that time isn't an absolute constant, but a flexible dimension that can speed up or slow down depending on how fast you're moving. Quantum mechanics shattered the classical view of particles behaving in predictable ways, showing us that uncertainty and probability govern the smallest scales of reality. These breakthroughs wouldn't have been possible without theoretical physics pushing beyond what we could observe at the time. The beauty of theoretical physics is that it's not constrained by the limitations of current technology. It dares to explore what's just beyond our reach. While we may not yet have the tools to experiment with ideas like quantum gravity, extra dimensions, or dark matter, the math provides a way to explore these ideas and lay the groundwork for future discoveries. That's why theoretical physics is so powerful. It gives us the blueprints for what could be long before we can touch it or see it. The impossible starts to become possible. Theoretical physics doesn't exist in isolation. It's part of a dynamic interplay between mathematics, experimentation, and technology. This relationship is what allows us to turn wild ideas into real-world breakthroughs. Take the discovery of the Higgs boson, sometimes called the God particle. Decades before we built the Large Hadron Collider, theoretical physicists predicted the existence of this particle through mathematical models that explained why particles have mass. But it took years of building and refining technology before we could confirm its existence in 2012. The math gave us the clue, but it was the technology that allowed us to see it. In this way, theoretical physics lays the foundation for experimentation. And as technology advances, we can test ideas that once seemed out of reach. This same pattern plays out in fields like cosmology, where theoretical physics predicts the existence of phenomena like gravitational waves, ripples in space-time caused by massive cosmic events. For decades, scientists searched for evidence of these waves. And finally, in 2015, they detected them for the first time using LIGO, a highly sensitive experiment based on Einstein's equations from nearly a century earlier. Without the mathematical predictions of theoretical physics, we wouldn't have known what to look for. And without experimental physicists and engineers working together, we wouldn't have had the tools to find it. The role of theoretical physics in pushing the limits of science is essential. It serves as a guide for future exploration, predicting phenomena we can't yet see or measure. Today, theoretical physicists are tackling some of the most fundamental mysteries of the universe, like the nature of dark matter, the behavior of black holes, and the possibility of multiverses. These ideas may sound like science fiction, but they're grounded in the rigorous framework of mathematics and logic. As we build better telescopes, more powerful particle accelerators, and quantum computers, we're constantly testing the boundaries of these theories. And with each breakthrough, theoretical physics will continue to push us further, asking the questions that take us from the impossible to the possible. The next frontier of science lies at the intersection of theoretical physics, mathematics, and technology. As we continue to ask the big question about the nature of the universe, the limits of physics, and what lies beyond the edge of our current understanding, theoretical physics will guide the way. It pushes the boundaries of what's possible, exploring new ideas and laying the groundwork for the revolutions to come. While we may not yet have all the answers, the beauty of theoretical physics is that it's always reaching further, challenging us to imagine a universe far bigger, stranger, and more beautiful than we ever thought possible. Imagine a world where today's impossible becomes tomorrow's reality. A world where we unlock the deepest mysteries of the universe, solve problems that have baffled us for centuries, and redefine the limits of science. That world may be closer than we think, thanks to emerging technologies that are pushing the boundaries of physics, computation, and material science. As we develop quantum computers, harness the power of artificial intelligence, and build more advanced particle colliders, we're beginning to explore realms that once seemed unreachable. At the same time, breakthroughs in superconductors, graphene, and other advanced materials are offering new ways to manipulate the physical world, creating possibilities we could only dream of a few decades ago. These future technologies could turn the impossible into the possible. Exploring, they might unlock new frontiers in science and reshape our understanding of what's achievable. Let's start with one of the most revolutionary tools in our arsenal: quantum computers. Unlike traditional computers, which process information in binary, ones and zeros, quantum computers operate using qubits, particles that can exist in multiple states at once. This ability to compute in parallel gives quantum computers the power to solve problems that are intractable for classical machines. Quantum computers could be the key to unlocking new physics, allowing us to simulate complex systems from the behavior of particles at the quantum level to the entire structure of the cosmos. Imagine being able to model the multiverse, calculate the dynamics of quantum gravity, or discover new particles hidden in the fabric of reality. These tasks, which seem impossible now, may soon be within reach. Next, there's artificial intelligence, a technology that's already transforming nearly every field of science. With its ability to analyze massive amounts of data, AI is helping us discover new patterns and relationships in the universe that we wouldn't have noticed otherwise. In physics, AI is being used to sift through vast amounts of data from particle colliders like the Large Hadron Collider, helping scientists identify anomalies that could point to new particles, forces, or even dimensions. AI systems are also being used to solve complex equations in quantum mechanics, develop new theories, and simulate the interactions between particles at levels of precision we've never had before. As AI continues to evolve, it will play an increasingly central role in expanding the boundaries of what's possible. And then there's the next generation of particle colliders. Machines designed to push particles to unimaginable speeds and energies. These colliders, like the Future Circular Collider or other proposed supercolliders, could take us beyond the standard model of particle physics, helping us discover new fundamental forces, exotic particles, or even hidden dimensions of space-time. The potential breakthroughs from these colliders could be profound, allowing us to solve the mystery of dark matter, understand the behavior of black holes, or even find evidence of extra dimensions that change our understanding of the universe. While quantum computers and particle colliders push the limits of theoretical physics, breakthroughs in material science are reshaping what we can do in the physical world. One of the most exciting developments in this field is the discovery of superconductors, materials that can conduct electricity without any resistance. Superconductors are already being used in applications like magnetic levitation and quantum computing. But their potential goes far beyond that. If we could develop room-temperature superconductors, it would revolutionize everything from power grids to transportation, allowing for frictionless energy transmission and levitating trains that move at incredible speeds. And then there's graphene, a material made of a single layer of carbon atoms arranged in a honeycomb pattern. Graphene is one of the strongest, lightest, and most conductive materials ever discovered. Its properties are so unique that it could completely change how we design everything from electronics to medical devices to spacecraft. Graphene's incredible strength and conductivity mean that we could build electronics that are smaller, faster, and more efficient than anything we've seen before. It could also pave the way for new energy storage technologies, like ultra-thin batteries that can store massive amounts of power, or solar panels that capture energy more efficiently than ever. The potential of superconductors, graphene, and other advanced materials is nothing short of revolutionary. As we continue to develop new materials with unprecedented properties, we'll be able to rethink what's possible in fields like energy, communication, and even space exploration. Imagine building structures that can withstand the harsh conditions of deep space, spacecraft that can harness solar energy with incredible efficiency, and quantum computers small enough to fit in your pocket. These materials could turn the impossible into the possible, changing the way we interact with the physical world. As we look toward the future, it's clear that impossible technologies may not be as impossible as they seem. With quantum computers, AI, advanced particle colliders, and breakthroughs in material science, we're entering an era where the boundaries of science are constantly being pushed and redefined. Each of these technologies brings us closer to answering the deepest questions about the universe and developing solutions to the greatest challenges we face. Whether it's discovering new particles, unlocking the mysteries of dark matter, or revolutionizing energy production, the tools of the future will allow us to go beyond what we once thought possible. The technologies of tomorrow will allow us to explore new frontiers, from the quantum realm to the farthest reaches of the universe. The impossible is no longer a barrier, but a challenge waiting to be overcome. As we continue to innovate, and we'll find that the limits of science are only the starting point for new discoveries that will reshape our world and open up possibilities we can't yet imagine. There's something about the impossible that captures our imaginations. It's not a barrier to progress, it's an invitation to explore. Throughout history, the things we once thought could never be done, flight, space travel, splitting the atom, have become part of everyday life. What was impossible yesterday is achievable today. So when we speak of the impossible, we're not really talking about limits, we're talking about frontiers. Frontiers are meant to be crossed, and the impossible is no different. It pushes us to ask big questions, to challenge our assumptions, and to strive for something greater. It's in this pursuit of the unknown that we find not only scientific discoveries, but also philosophical insight about who we are and what we're capable of achieving. Today we'll explore how the impossible isn't a wall we can't scale. It's an invitation to push the boundaries of our knowledge and redefine the world as we know it. When we think about the impossible, it's easy to view it as a barrier, something that can't be crossed, an idea beyond our reach. But the truth is, the impossible is nothing more than a frontier waiting to be explored. Throughout history, we've faced countless challenges that seemed insurmountable, and time and again, we've found ways to overcome them. Consider the idea of heavier-than-air flight. For centuries, the notion of humans soaring through the skies seemed absurd, an impossible dream. But in 1903, the Wright brothers proved that, with the right technology and persistence, flight was not only possible, it was inevitable. Space travel was once considered a fantasy, too, but in 1969 we landed humans on the moon. These once unthinkable achievements show us that impossibility is often just a matter of perspective, waiting for the right moment in history to be overturned. The impossible becomes possible when we look at it as a challenge, a frontier where new discoveries lie just beyond the horizon. And these frontiers aren't just about technology or science. They're about human potential, our ability to imagine, to create, and to transform our world. The impossible invites us to dream bigger, to push the limits of what we think is achievable, and to open new doors to innovation. Exploring the impossible isn't just about solving problems. It's about unlocking deeper truths about the universe and ourselves. Every time we venture into the unknown, we learn something new, not only about the world around us, but about the nature of reality itself. This is where science and philosophy come together. When theoretical physicists propose new ideas, whether it's about multiverses, dark matter, or the origins of the universe, they're doing more than just experimenting. They're asking existential questions. What is the universe made of? Why are we here? What are the limits of knowledge, and can they be surpassed? These questions don't just fuel scientific discovery. They push us to think about the meaning of existence. As we explore the boundaries of physics and test the limits of impossibility, we're also exploring the limits of human understanding. Each discovery brings us closer to a deeper philosophical insight into who we are and what the universe is capable of. The impossible, then, is not just an obstacle to be overcome, it's a guide, leading us to new ways of thinking, new possibilities, and new ways of understanding our place in the cosmos. One of the greatest lessons of history is that what seems impossible today is often achievable tomorrow. In every generation, there have been limits that seemed unbreakable, ideas that were beyond the reach of human knowledge. And yet, time and again, those limits have been overcome. Think about electricity. Before the 18th century, people lived without electric lights, relying on fire for heat and light. Today, electricity powers almost every aspect of our lives. Or consider computers. Once massive new room-filling machines that could only handle simple calculations. Now, we carry supercomputers in our pockets. These shifts in technology weren't just advancements, they were paradigm shifts. Changes in the way we view and interact with the world. The same could be true for the impossibilities we face today. Whether it's faster-than-light travel, harnessing infinite energy, or understanding the true nature of quantum mechanics, these challenges are not barriers, they're opportunities. What seems impossible now may be the breakthrough of the future, waiting for the right combination of knowledge, technology, and vision to make it real. History teaches us that limits are temporary, and the impossible is often just a matter of time. The future is filled with possibility, and the next great leap forward may be closer than we think. The impossible isn't something to fear, it's something to embrace. It challenges us and inspires us and drives us to explore the unknown. It invites us to push beyond the boundaries of what we know, to imagine new worlds, and to seek out the truths that lie just beyond our reach. As we continue to explore the frontiers of science and technology and philosophy, we'll find that the impossible is not a final limit, but a starting point for the next great adventure. What we discover tomorrow will reshape our understanding of the world, opening doors to possibilities we can't yet imagine. The impossible is not the end, it's the beginning of everything we have yet to achieve. As we come to the end of our journey through the world of the impossible, we find ourselves at the intersection of science and philosophy, two disciplines that, together, seek to unravel the mysteries of the universe. Both science and philosophy ask profound questions about the limits of reality, exploring not only what we know but also what we don't. They challenge us to consider whether the impossible is truly beyond our reach or simply the next step in our quest for understanding. In science, the impossible is a frontier, a challenge that pushes us to innovate, to experiment, and to expand our knowledge. From quantum mechanics to the exploration of black holes, science has consistently redefined what's possible, turning once impossible ideas into the foundations of modern technology. In philosophy, the impossible raises deeper questions. What are the true limits of human knowledge? Can we ever fully understand the universe, or are there some truths that will remain beyond our grasp? Together, these approaches offer us a way to understand the impossible, not as an unbreakable barrier, but as a spectrum, a constantly shifting horizon that moves as we make new discoveries. Throughout this journey, we've explored the concept of the impossible through three distinct classes of impossibility. The first one is Class 1 impossibilities, technologies that seem impossible today, but don't violate the known laws of physics, like invisibility cloaks and teleportation. These ideas are within reach, and with advances in quantum mechanics and material science, we may see them become reality sooner than we think. Next one, Class 2 impossibilities. These are technologies at the edge of our understanding, such as faster-than-light travel and time travel. While they challenge our current knowledge of physics, they remain within the realm of possibility, awaiting breakthroughs in our understanding of space-time and quantum gravity. The last one is Class 3 impossibilities. These are the true impossibilities, like perpetual motion machines, ideas that violate the fundamental laws of physics as we know them. But even here, history reminds us to be cautious. As we've seen with relativity and quantum mechanics, what seems impossible in one era can become possible with new insights and understanding. As we've seen, each of these classes of impossibilities serves as a reminder of how science evolves. What was once science fiction can become science fact. The limits we see today may simply be challenges, waiting for new perspectives, new experiments, and new ideas to break through. This leads us to the ultimate question. Are there any true limits in nature? Is the impossible simply a reflection of what we have yet to achieve? Or are there certain boundaries that we will never cross? Unchangeable laws of the universe that define what can and cannot be done. If there are true limits in nature, we haven't found them yet. The history of science is filled with examples of overcoming perceived boundaries, from the discovery of relativity to the unraveling of the quantum world. Each time we've encountered a limit, we've learned that it's not an end, it's a beginning, a point from which we can expand our horizons and imagine new possibilities. And yet, as we venture further into the unknown, exploring concepts like dark matter, quantum entanglement, and the nature of time, we may find that there are mysteries that remain unsolved, perhaps forever. But even if we reach a point where certain truths lie beyond our reach, that won't stop us from trying to understand them. The impossible, then, is not just a challenge, it's an invitation to keep exploring, to ask new questions, to build new technologies, and to search for answers in places we haven't yet imagined. The true spirit of science lies in curiosity, in the belief that no matter how far we've come, there's always more to discover. So, are there true limits in nature? Perhaps. But for now, the impossible is simply what we haven't achieved yet. The impossible is a frontier, a boundary that moves as we move, expanding as we expand our understanding. What we discover next will reshape our world and redefine the impossible once again. And as we stand at the edge of this vast unknown frontier, we are reminded that the journey of discovery is never truly over. It is in fact just beginning.